sleep-inducing as well. And if you are learning this or are reviewing, I hope that this is just a nice, encouraging, I don't know, just like a loving extra resource for you. This isn't meant to replace anything that you might already have or are following along with. I just hope that this is a nice kind of way to support and love you. So, and I do. But I do. So, we're going to take our time here and let's see what we come up with, okay? And as always, there's never any pressure. I just want to remind us here that there's never any reason to compare, because there's always going to be someone who knows more than you, and there's always going to be someone who can use your unique way of explaining things. So right here, right now, let's just let go of all of that and just enjoy and be in this moment, okay? So I am going to start by just drawing a typical setup for the law of signs, just to make sure we're on the same page here. But again, I've made a video on this before, so we're going to kind of move a little bit quicker for this part. So I'm just going to draw a random triangle, like so. I'll just call it A, B, and C. So we have three angles, three interior angles, like so. So I'll just call this angle A, angle B, angle C. And we label the lengths of the sides that are across from each angle with the lowercase of the respective letter. So for here, the length of this side, which is across from angle A, is going to be little a. Across from angle B is little b. And across from angle C is little c. And the letters themselves are completely arbitrary, but this helps us keep the proportions from the law of signs straight. So when we write this out, we have little a over sine angle A equals little b over sine angle B, and little c over sine angle C. So, and you might use the reciprocal of this, so you might have sine A over little a equals sine B over little b equals sine C over little c. Mathematically, that's equivalent. It's okay. But we're going to leave it like this. And so this just gives us a way to fill in more information when we're given some of this information. So if, for instance, we are given angle A and angle B and the length of the side across from A, we can use this proportion to solve for B algebraically. Or you can use, any two of these three. And we can also use other regular geometry facts that we know, such as the fact that the sum of the interior angles of a triangle must add up to be 180. So if we have angle A and B, then we can find angle C and use this part of the proportion as well. So we can have fun with that, and it really just depends on what we are given. So with the law of signs, though, if we are given angle A and B, or any two angles, and one of the opposite lengths, that is the most straightforward situation for the law of signs. We just plug and chug and maybe do some cross multiplication or just some basic algebra to solve for the length of the other side. It's clear, not ambiguous at all. Where things might become ambiguous is when we are solving for an angle. So if we're given a side, and an angle, and we're trying to find the other angle here within these four, that is a potential case for the ambiguous situation. And again, as a function, this is basically just the idea that if I have, let's say, sine of b equals some type of value, let's say it's positive, if I'm looking from 0 to 180 for b on that domain, there is potentially two values for b that gives me that same positive value, and that's because on the unit circle, the sign of an angle corresponds to the y coordinate of the xy point that is corresponded to this angle b, and that's a mouthful to say out loud, but if you need to go back with your unit circle, that's okay. But with any angle, let's say this angle, there's a point on the unit circle that corresponds to that. When you start with 0 and you move this way counterclockwise to your point, that's your xy, and the sign corresponds to the y coordinate. It's basically the opposite over hypotenuse, but the hypotenuse being 1 on the unit circle. So you have two values that can both give us the same sine b value, and we're looking at only from 0 to 180 because of our triangle, our angle here. It's not going to be 0 because we actually have a triangle. It's not going to be 180 because 180 is a straight line. So it's going to be between 0 and 180, and depending on the way that we draw our triangle and the given information, we might end up having these two possible angles for B. So if I'm given A, B, and this angle A, this B might not end up being here. We might have two possible triangles that satisfy the same A, B, and angle A, if that makes sense. That's just kind of the big picture. Let's actually draw out a situation first to see how the math works out, and then we'll talk about when, more specifically, the conditions when this might happen, okay? So let's say we have, this is my protractor, so I might as well use it. So I'll label this, line it up. So we have 0 here, 10, 20, 30. Let's do 34 degrees right here. And let's say we have, like, this won't be completely to scale, but let's do something like this. Okay, so I'm drawing this down like this as though I know, but we're actually not sure. Let's say we have 34 degrees, A, B, C, and let's say I have 7 and 10. So we have side, side, and angle, and we want to figure out what this angle is or might be. So we would do 10 over sine B equals 7 over sine 34 degrees. Or if you want your unknown on the top, that's fine too. Sine B over 10 equals sine 34 over 7. Totally fine. This is fine. So I'm going to go ahead and cross multiply. So 7 sine B equals 10 sine 34 degrees. And then I'm going to move the 7 over here by dividing it on both sides. Just a little bit of algebra here. So 10 sine 34 degrees over 7. And so let's go ahead and type this into our calculator so that we have some concrete numbers to work with to get the idea. is at the horizontal right here, or not the horizontal, the diagonal right here is 45. This is 90, so 53 might be right here or so. So the y coordinate of this point is 0.79885, but we can actually also reflect that over here, and that would be 180 minus 53, which is 127, right? So 127 degrees actually also gives me the same sine value. Look at that here. Let's do sine of 127, and we're rounding a bit, right? So sine of 127 is 0.7986, so close enough, right? We rounded a little bit with this 53, but that's good enough. So 127 also works for this function. So what that means is we actually have two possible b's that give us 10, 7, and 34. So this angle, it's acute, so this would be our 53-degree situation. But 127 kind of implies that we have an obtuse angle here, and basically what we're doing is taking this and kind of swinging it here, taking this 7 because the information is 10, 7, and 34, but the other angle would be kind of taking this and swinging it here like this, so that this triangle is, or that angle is 127. That also works. So if you see here, we have two triangles, one being this possible, given a length like that and a length like this. I have one possible triangle like this, but I also have a possible triangle like this. A, C, and B down here. Does that make sense? So we have one big triangle like so, and we also have this because this could also be 7. So that's the ambiguous case. Two possible triangles given the same, we'll call it given A equals 7, B equals 10, and angle A equals 34 degrees. This is ambiguous. This angle B is the ambiguous case. So just kind of intuitively here, without using this sine function idea, just algebraically, basically, if we take the 10 and let's make that solid 10, because we're given this angle here, so this part is like given in concrete. The 34 is given, the 10 is given, but the 7 is kind of what swings here. We're not really sure. So that's the part that's kind of variable, and that gives us the different scenarios. So if I have that this number is greater than this number, so let's say this is like 13 or something, as long as you have and satisfy the triangle inequality, there's one triangle that would exist there because it just kind of hits, there's nowhere to swing. But if we take this 7 intuitively here, basically, if we kind of move this, we kind of take this as like a little hinge up at the top or something and swing this over here, if we have enough room to make this other angle here while keeping this 180 sum, then we have this ambiguous case. So you can use the fact that sine B has there are two B values from 0 to 180 that gives you the same sine B, but you also want to make sure that given the angle that you have, that sum is not already 180 because you wouldn't have room for this angle C here because we still need the sum to be 180. So if this sum is less than 180, in this case we have 161, right? So that leaves us plenty of room for angle C to exist. So that's the idea. If we take this 7, but we can also have a 7 here. So 2 answers, and the 2 angles are supplementary. Supplementary meaning that they add to 180 degrees. Okay, perfect. So now we can kind of take a look at the conditions for when it's possible to have this ambiguous case, right? So intuitively and kind of algebraically here, it kind of looks like we have this 10 that is set in stone given this 34 degrees. We have this 10, and let's just say that that's locked in. You can kind of see that it's really this 7 side, this B side, that can vary. It can either be here or here. So basically, if this angle, if I do 180 minus that angle to get this 127, if I happen to have 34 plus 127, which is 161, right? That is less than 180. That leaves enough room for another triangle or another angle here. So we would have 2 possible triangles. So in general, if I have sine B equals some value from 0 to 180, if it's positive, I have 2 possible angles always. But if, as long as it's not, the 90 degree, which is just 1, I'll have 2 because I can reflect in quadrant 1 and 2. But that doesn't necessarily mean that they fit into separate triangles, because if the angle is really big, let's say here, if we have, let's say, 150 degrees, 150 plus 34 is already 184, which leaves no room for this angle C. So in that situation, we would not have an ambiguous case, because it doesn't really leave room for this third angle here. There would just be one triangle. So what we look at then is basically the sine. We did the sine inverse, we did the 180 minus, and we check to see if the sum of our angle A plus this other angle, if that leaves enough room for the total sum to equal 180. That's another way of looking at this ambiguous case. But let's look at the actual conditions for when this might appear. So if you see that we have 10 set in stone, that's A, and angle A is 34, then you can kind of see that it's the 7 that's kind of swinging here or here, right? And so naturally what I'm going to do is kind of want this boundary line or this boundary segment to compare it to, which when we're dealing with triangles or anything to do with trig, kind of makes us want to look at a height. We want right triangles. So I'm going to draw the height of this triangle. So in this case, we'd compare it to the height, which is taking from C and drawing straight perpendicular down. Okay, so we can calculate what that is. This is H. In this case, H would be, you can just use SOHCAHTOA. So sine of 34 is H over 10. Opposite over hypotenuse. So sine 34 equals H over 10. So H equals 10 sine 34 degrees, which is approximately 10 sine 34 is 5.59 this value, 5.592, then we wouldn't even have a triangle to begin with. That would be a problem. So we would have something smaller than this because we have a right triangle here. If this is the hypotenuse can never be less than the length of one of the sides because of the Pythagorean theorem for one. It can't be equal or less because then this would have to be a negative, or it's imaginary. It wouldn't work at all here. And it can't be equal because if this equals h, then the hypotenuse and the leg would be h, which means this length would be 0, so we wouldn't have a triangle at all, right? So basically, if if this 7 equals h 5.592, then when we do the law of sines, it literally is the one right triangle. So we would have one triangle, not ambiguous. If we have this length a is less than this, we said there's no triangles. And if we have this a that is less than this but bigger than 5.592, so this a needs to be less than 10 but greater than 5.592, that would be our candidate for our ambiguous case, okay? And if we somehow have this a value is bigger than 10, let's say it's like 12 or something, there will be definitively one answer as well. There will only be one triangle. So the actual condition is this a being less than b but greater than h. So it's got to be a is less than b, or a which is less than b. That would be the main condition for checking for our ambiguous case, okay? So h being the height of our triangle, which you can use just SOHCAHTOA to calculate, and if we have this a value bigger than this but less than this, then it kind of looks like we would have this swinging case, this copy and paste case, which is always going to be the angle and 180 minus the angle. And if you just want to do this algebraically, just go ahead and do the sine law, take your inverse sine, but just also check 180 minus whatever angle you're working with and see if you add that to your original angle A to see if that is less than 180, then you have room for angle C to exist, which means you have two possible triangles. That's it. I know that the ambiguous case confuses a lot of people. I hope that this kind of starts building some of that intuition. It's this idea of having an angle locked in place, having a length locked in place, and then if this a length kind of fits these conditions, it kind of has room to exist in